Good afternoon, everyone. How are you today? Okay, not so good, right? Okay. It's a raining day. Okay. On Monday, we talk about bypass, and I just give you one of the example. Today, you have a better understanding of the uh, bypass. This is a heart, right? So if the heart has this is kind of we call bypass surgery. For example, if you have a blockage in this vessel, in this blood pipe, and then in order to let the blood go through easily to the heart, you need to have a bypass. And then before you, so this is one of the method of the bypass, right? This is also the bypass. This stream is also the bypass. Okay, so just that you know that the meaning of the bypass. So let me make a conclusion of the this part, recycle and bypass. So this is the process, for example, and if the stream go to this way from the entrance, from the input, and split up to two streams, and this one stream goes past this process and go to join the end of the output stream. This is what we call bypass, right? Bypass stream. However, if the stream come from the output and go back to the input and join the input stream together and move it to the process, and this is what we call recycle. Okay, so the calculation of the bypass and recycle process, which is exactly the same as that we do the calculation of the multiple single or multiple units, because that we can regard this as a kind of join point, which is a single unit process, right? And then this single unit, and this is a kind of join point of the two streams. So this can be regarded as a unit, single unit too. Okay, so the system we want to consider here is that again, we think of the overall process first, and after that we think of the single unit process, right? This is one of the single unit process. This is another single unit process. This is the third one, third single unit process. Okay, and then after that we do the stream mixing point. This stream mixing point, and this is stream mixing point, and this is stream mixing splitting point. This is stream mixing point. And one of the very important point here I want you to remember is that if we have a splitting point like this part, the fraction of this one and this one will be the same, right? Fraction will be the same. So you need to remember, if you have a splitting point here, the fraction of this and this will be the same, although the amount of these streams will be the different, right? Okay, so this is one of the important points you need to remember when you do the mass balance calculation. Okay, so this is what we have learned on Monday. So today, let's move to a new topic, which is we want to know that if the mass balance involve chemical reaction, what can we do? Can we do input equal to output, or can we shall we introduce consumption and generation into the general balance equation? But before we talk about this, section 4.6 is about chemical reaction stoichiometry. I'm sure you have learned this when you are in high school, but let's have a quick review about chemical reaction stoichiometry. And after that, we move to mass balance. Mass balance including the chemical reactions. Okay, so we understand that chemical reaction stoichiometry is that if we have A and then become B. This is A species, and after chemical reaction become B species. Obviously, we need to use a reactor for this chemical reaction. So, and then before that, we know that we have input and output. However, because you generate new species, which is B, so you need to have you need to introduce a new term called generation here. Generation here. Why? Because originally you only have A species, and now because of chemical reaction, you create a new species called B. So you have terms of the generation in the general balance equation. Okay, and after that, you know that you consume some of A because you need to consume some of the A in order to create or generate B species. So you have something like consumption. It consumes some of the A species. Okay, and if this process is in a steady state condition, then there's no accumulation in the reactor, either A or B species. Okay, so that's why the general balance equation will become input plus generation minus output minus consumption equal to 0, because it's supposed to be equal to accumulation, because but as I just told you, this is a steady state process. If this is a steady state process, then we will remove the term of the accumulation. Okay. Right. So section 4.6a, we talk about stoichiometry first. So what is the definition of the stoichiometry? So stoichiometry is a theory of the proportions in which chemical species combine with one another. And this is a Chinese explanation here. I'm sure you all understand. For example, if we have A and B in the input and go through the reactor, we come out with C and D. So in the end, we will have not only C and D but also A and B, because the conversion it cannot be complete, might be not be completed, right? So we have output of A and B. It can be, you might have B, A and B. You might have B only. You might have A only. Okay. So stoichiometry, that there are some information about stoichiometry. So measuring chemicals that go in and come out of any given reaction. In Greek, stoichiometry means what? Measuring elements. Okay? Measuring elements. Allow us to count atoms and molecules by weighting them. So if you have this stoichiometry, you want to know the relationship between input and output, and we want to count the amount, or want to weight the amount of the input and output. So the first thing we want to introduce you here is called stoichiometric equation. What is stoichiometric equation? The definition of stoichiometric equation is that a statement of the relative number of molecules or moles of the reactants and the products that participate in reaction. I'm sure you understand this because we have Chinese here. Okay, for example, if you have two moles of the SO2 plus 1 moles of the oxygen molecule, and it become 2 moles of the SO3. It makes sense, right? It makes sense. This is what we call stoichiometric equation. Stoichiometric equation. Okay. Okay, so the second term we want to introduce you is stoichiometric coefficient. What is stoichiometric coefficient? For example, as I just showed you in the previous slide, 2 moles of the SO2 plus 1 mole of the oxygen molecule become 2 moles of the SO3. So what is stoichiometric coefficient? This is, we understand that in order to have a complete description of this equation, the oxygen on the right-hand side should be equal to the oxygen on the left hand side, on the left. Okay, so for example, and the sulfur on the left needs to be equal to the sulfur on the right. So for example, if you have one oxygen here, so you have 4 oxygen atoms and plus 6 oxygen atoms, then need to be equal to 6 oxygen atoms on the, from the left, from the right, right? Okay, so how can we do that? This is what we call, we need to put the numbers in the front of this equation. And 2, 1, 2, 2 is what we call stoichiometric coefficient. Okay? Okay, the third term is called stoichiometric ratio. What is stoichiometric ratio? Stoichiometric ratio is that you have 2 moles of the SO2 and you have 1 mole of the oxygen. So if we want to know, if I want to tell you that, well, please tell me what's the stoichiometric ratio of the SO3 to the oxygen, O2. Then what's that? That will be what? That will be 2, right? Because you have 2 moles of SO3 and you have 1 mole of O2. So the stoichiometric ratio will be 1. Sorry, it will be 2, right? Because 2 divided by 1. Okay, this is what we call stoichiometric ratio. How about SO2? The stoichiometric ratio of the SO2 to SO3. That will be what? That will be 1, right? That will be 1. This is, I'm sure you learned this in your high school or junior high. Okay, so this is example here is the stoichiometric equation. We understand this is the stoichiometric equation, right? So let's make example. 1,600 kilograms per hour of SO3 is to be produced. This means that this one needs to be produced 1,600 kilograms per hour. Max production, continuously. Continuous process, as you know that there's an hour, right? So this is continuous process. Okay, calculate the amount of oxygen required. If you cannot solve this problem, I suggest you to go back to junior high school, right? Okay, so first of all, you need to know the molecular weight, and you need to compare. You need to know how many molecules you need to produce, right? How many moles of the SO3 you need to produce, and by stoichiometric ratio, you know that how much amount of the SO2 required, how many amount, what's the amount of the O2 required. Okay, so this is the amount of oxygen required here. So please, I think you can work out this with me, by yourself, right? Okay, so this is molecular weight, and you understand, you know how many moles of the SO3 need to be produced. And because of stoichiometric ratio, you know that if you produce 2 moles of SO2, you need to consume 1 mole of oxygen. So as a result, you got this number. Okay? 10 moles. Right, so this is what we call dimensional equation. I hope you still remember. Dimensional equation, you need to put the unit, so it's easier for you to do the calculation, right? And this is called stoichiometric ratio. And okay, so let me summarize the 4 terms here. The first one is called stoichiometry. Is that it's kind of, we are talking about this kind of study, right? Right, so this is what we call stoichiometric coefficient 2, 1, 2. This is stoichiometric coefficient, right? Okay, how about stoichiometric ratio? 2, 1 or 2, 1, 1, 2. This is called what we call stoichiometric ratio. And then in all, this is called stoichiometric equation. Okay? So this is very easy. Very easy. Right. So let's move to a more college level of the study. Okay. So 4.6b, based on this equation, we want to know which reactant is the limited reactant, which reactant is excess reactant. Okay, so if we have these 4 topics in the section 4.6b. So if you have this equation, could you please tell me which one should be the limited reactant? Which one should be the excess reactant? Do you know that? Normally, I just want to give you a hint. Excess reactant normally is the cheaper one. You know, you want to have a cheap products, and you don't mind you put more to the equation to the reactor. So normally, if you think of this, which one is cheaper, SO2 or O2? Which one is cheaper? O2, right? Because you just put the air in. Because air contains 21% more of the oxygen. So you just put all air in, and then this will be excess reactant. This one will be limited reactant. However, how much, and then we want to introduce you another 2 terms. The first one is called fractional conversion. You understand that SO2 plus O2, if you have a complete conversion, that means everything will, all of the SO2 will be consumed to become SO3. But unfortunately, for some reasons, you don't want to complete this reaction because you run out of your time. Or you just want to break it, you want to stop it when the conversion rate becomes 80%, right? I think we have talked about this on Monday and before the midterm exam. So this is what we call conversion, fractional conversion. And the final term we want to introduce you is extent of reaction. Extent of reaction. Okay, so let's start from the first and the second terms. So assume we have a reactor and we want to consume SO2 and to make SO3 as a product. So we have input, right? We have 2 moles of SO2 into the reactor, and we have 1 mole of the S1 oxygen into the reactor. So you will understand, right? Well, this matches the stoichiometry ratio. So you need, if you have 2 moles of SO2, obviously it required to have 1 mole of oxygen. And as a result, there are 2 moles of the SO2 come out from the reactor. Right. So the ratio of the input will be 2 to 1. Okay? No problem. So if there are two circumstances. The first one is if the ratio of the input equal to the stoichiometric ratio. That means what? This is what we call stoichiometric proportion. So 2, 1, you put 2 moles of the SO2 and exactly 1 mole of oxygen. And this is what we call stoichiometric proportion. However, if we don't do it in this way, we have one extra. We put 1 more. We put something cheaper. Put reactant, which is we put more into this reaction. So this is why we use up some of the reactants. This is called and the one used up first is called limited reactant. Okay. And another reactant is called excess reactant. Okay. Easy. And then now we want to know the fractional excess. Fractional excess. For a fractional reactant is that the definition of fractional excess is that the moles of the reactant fit into the reactor minus the moles of the stoichiometric. divided by the moles of the A species, which is in the stoichiometry ratio. Okay, what can we do for this? I just here. So this is the definition. So let me give you an example. Is that if I have 1.5 moles of the oxygen fit into the reactor, and actually in the end, because these 2 1, so you just only consume 1 mole of the oxygen, which is stoichiometry, right? And then this, and also you have 1.0 oxygen stoichiometry. So the excess reactant will, fractional excess will be what? Will be 0.5, right? 0.5. Okay, I want you to remember the definition here because this might be the Kahoot next week. Okay, you need to remember the definition. So the fit and the stoichiometry ratio. Okay, I will give you more examples later. So let's practice. So the fractional conversion is that in chemical reaction does not take place instantaneously, and indeed often proceed rather slowly. So if the chemical reaction process very slow, you don't have time to wait. So you might stop before you complete the reaction. That's why we need separator, right? That's why we need separators to separate A and B, for example. In such cases, it is not practical to design the reactant for a complete conversion of the limited reactant. For example, you don't want to, it takes long time to do the completion of the reaction. And then you don't want to wait, so you just make a separator to separate A and B. Something like this. So the influent emergence with the sum of the limited reactants still present and its length usually subjected to a separation process, this one right here, and then remove the unconverted reactants from the product. The separated reactant is then recycled to the reactor inlet. That's what we learned on Monday, right? So this is, so the fractional conversion of reactant, this is another one, is called moles reacted divided by mole fed. So you might say, wow, Professor, something wrong, because in the previous slide, this is called fractional excess. You need to distinguish the fractional excess and what we call fractional conversion. These two are very different concepts. These two are different concepts. Okay, so this is another definition you need to remember. The fractional conversion of a reactant, moles reacted and moles fed. For example, sulfur dioxide here, sulfur dioxide, if you have, of course, you have if you put 100% here, that will be the percentage. Okay, so here, for example, sulfur dioxide, if you feed 3 moles of the sulfur dioxide into the reactor, and in the end, you only consume, you feed the 4 moles of the sulfur dioxide into the reactor, and in the end, you only consume 3 moles sulfur dioxide. Then the fractional conversion will be what? Will be what? 75%, right? 0.75. But if you put 100% here, the percentage conversion will be 75%. Okay. Right. So I want you to remember these two definitions, and I might give you an example in a Kahoot in next week. Okay. So please remember this: fractional excess and the fractional conversion. And if you just use this example, I'm sure it will be easier for you to understand. Right. So now I just give you an example. I think I don't want to read the text with you together. So here I just want to tell you that this is chemical reaction. C2H2 plus 2H2 becomes C2H6. Obviously, you know that hydrogen will be grabbed on the C2H2 ethylene, ethylene, right? So before reaction, we have 20 kilomoles of the C2H2. And then we have 15 kmoles of the H2 hydrogen. And in the beginning, we have 50 kmoles of the C2H6. Okay, this is text. And then in the process of reaction, that we understand there are 30 kilomoles of the hydrogen was consumed. So as you know that if there are 30 kilomoles of the hydrogen was consumed, and how many moles of the H2O2 will be consumed? That will be what? 15, right? 15 kilomoles of the H2O2 will be consumed. And how many moles of the C2H6 will be generated? How many? 1, right? Because follow the stoichiometry ratio, you understand this will be 15, right? 15. So as a result, you understand in the end, you have, after reaction, you have what? You have 5 kilomoles of C2H2. And you have what? You have 20 moles of the 20 kilomoles of the H2. And you will have 65 kilomoles of the C2H6. And now I want to ask you the fractional excess. You know, for the C2H2 and the hydrogen, which one is excess reactant? As you can see here. Obviously, hydrogen is cheaper, right? Hydrogen is cheaper. And as you can see that if you have 20 kilomoles of the C2H2 and you only consume 40 kilomoles of the hydrogen. So obviously, hydrogen will be the excess reactant. And if I want to ask you fractional excess, this is the question. This is the equation, right? So could you please tell me what's the number of feet and minus what? Stoichiometry minus what? And divided by what? Can you tell me? You know, you fit 50 kilomoles, right? And then according to this equation, the stoichiometric equation, and then you know how many hydrogen need to be consumed. If it is 20 here, you need to be 40. Right? So you had to divide, you had to minus 40. And for the moles of the stoichiometric will be what? Will be 40. Okay, so this is the answer. And how about the fractional conversion? Please do this by yourself, okay? Okay, I can tell you I can ask you the fractional conversion of the C2H2 and the fractional conversion of the H2, right? You can tell me. Right, so why we need to form the why we need to form SO3? Because we want to make sulfuric acid, 硫酸. We need to make sulfuric acid through this equation. Okay, so the formation of the SO3 from the S2 and the O2 is the intermediate steps in the manufacturing of the sulfuric acid. And but you know, it is also responsible for the acid rain phenomena. If you release SO2 to the space, to the environment, this environment, and together with oxygen, and then if it become SO3 and water come, it become sulfuric acid. So that's what we call acid rain. Acid rain. However, for the industrial, we need this process in order to make sulfuric acid. Right. So the general rules for the calculation, according to the previous topic, you need to know. And you know, when you when you are in the high school, this is probably enough for you to know that. But when you are in the college, now you are in the college, so some of the complicated uh, problems you need to solve, and you need the help from the computer. So you need to do the computation, and then you need to know some skills. So that's why here we want to introduce you how to do the calculation. But there are some general rules you need to know. The first one is called extent of reaction. We use this symbol we call XC. 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 It can be a it can be the it can be this is a kind of Greek symbol, okay? Greek symbol. We call it XC. So let's make this is the stoichiometry equation as we know in the previous slide, and C2H2 plus 2H2 becomes C2H6. So what is before reaction? We know that we have in the beginning we have originally moles of the reactants and and also the products, right? The product. And after reaction, what's the base of the reaction? So we know that if we have an external reaction, we call it XC, and because this reaction will do the consumption of this reactant, so we use minus here, -1. So according to stoichiometry ratio, if this is 1, that will, and for C2H2 that will be 0.5. So this is kind of a reaction. What's the degree of the reaction? It can be 80%, it can be 0.6, it can be 0.8. Okay, and then now you have 0.5 here because what? Again, this you have to meet the requirement of the stoichiometry ratio, right? 2 to 1, right? 2 to 1. Okay, so here the point is that you have a symbol here called XC, and this XC is external reaction. So after reaction, how can we write for the reaction? We know that after reaction, this will be deducted 0.5 XC, right? This original amount of the before reaction, you'll be minus 1 FC, and this will be plus 0.5 XC. Okay? So this is what we call external reaction. So external reaction, there are two symbols here. The first one is this XC is mole, right? If you have XC over dot, what does that mean? It's kind of flow rate, right? If you have a dot, it means flow rate, right? If you have V over dot, this is what we call volumetric flow rate. If you have M over dot, this is mass flow rate, right? If you have N over dot, that means what? Molar flow rate, right? Okay. Right, so this first term, XC, you need to know. And the second symbol we want to know is called nu. Nu is called stoichiometric coefficient. This is, remember that 1, 2, 1, this is coefficient. So nu is related to this one, 1 and 2 and 1 here. So this symbol is that C2H2 will be -1 because this is a kind of this is reactant. So the symbol need to be negative, right? How about hydrogen? Hydrogen will be 2, right? And it need to be -2 because this is reactant, which is negative. Okay, and then how about C2H6? This is plus because it's products. and it's positive. So for the product, the symbol need to be positive. For the reactant, the symbol need to be negative. So nu C2H2 will be -1, nu H2 will be -2, and nu C2H6 will be +1. Okay. So again, for the input and output, input is that NiO, this single I is related to the species. Okay, I species. It can be C2H2, it can be H2, right? Okay, it is small. And the Ni over dot is the I is species, and for the outlet. So this is the kind of symbol we need to remember. You might say, wow, Professor, why we need to do this? That's because when you do the computation, all the numbers, all the definition, you need to have a symbol to define something. So when you write coding, when you do the kind of write some programs like Python or something, you need a symbol to represent this, to represent how to let computer understand. So as a result, all the products, all the chemicals has input and output. So this is output equal to input plus nu times xc. Right? Output equal to nu. Output equal to input plus nu times xc. And here I just want to give you an example in the previous slide here. Is that for the example of the C2H2, the output, which is after reaction, will be equal to this one, right? Input plus nu times x, and this is what we call minus 0.5 means what? Output, stoichiometric coefficient. X means external reaction. So this is the one, ladies and gentlemen, this is the one I want you to remember. Output equal to input plus nu times xc. Xc is external reaction, nu is the stoichiometric coefficient. Okay, so all the chemical species follow this equation. Okay. Right. So let me summarize the general rule of the calculation. Is that, for example, if again, let's repeat what we learned. C2H2 plus 2H2 and become C2H6. So before reaction, we all write in symbol in this way. Okay, so this is input. We have blanket O. O means initial, right? And then during the reaction, we understand is nu times xc. This nu will be -1. This nu will be -2. And this nu will be +1. +1, right? Negative, negative, positive. And after reaction, we know that in the end, after reaction, that will be this one plus this. Right? After reaction, hydrogen will be this one plus this. And you know that C2H6, that will be this one plus this. All we know is output equal to input plus nu times x. Output equal to input plus nu times xc. Okay? Of course, if this is a continuous process, you have overdot here in the symbol, right? Overdot in the symbol. Right. So this is an example I want to show you here. A fractional hydrogen conversion is what's the fractional conversion? We know that it's called Xe, right? It's 0.6 So this is nitrogen plus hydrogen become ammonium. And this is a great invention. I hope you still remember. Under high temperature and under high pressure, you can create this. And then what is this for? Does anybody want to tell me what is this for? Ammonia, what is this for? This is a great invention. Why? Why this is a great invention? Because this save life. This is kind of you can make a lot of chemicals through this ammonia, especially what? Fertilizer, right? Okay, 肥料. Okay, you can make 肥料 for it because using this ammonium. Right, the fractional hydrogen conversion is 60%. So we understand that this is a kind of reaction that you don't want to have this. You need to have some argon into this reaction. Okay, so before reaction, we have 100 moles per second of the nitrogen into this reactor, and we have 300 moles of the per second of the hydrogen into this reactor. And in the very beginning, we have 0 moles of the ammonium, and we introduce 1 moles of the argon into this reactor. Okay, and then during the reaction, we understand because of hydrogen conversion rate 0.6, so this one need to times 0.6. That means there's only 180 moles of the hydrogen per second consumed in this reactor. So obviously, you understand then how many nitrogen will be consumed, how many ammonia will be generated, right? Okay, so as you know, if this 3 moles and you only need 1, there's only 1 mole consumed. So 180 need to divide it by 1/3 times 1/3, right? Times 1/3. That means 60. And how many ammonia generated? Easy, right? 120. 120. Okay, and this is inert gas, so there's no consumed or generated. Okay, so after reaction, you understand that this will be equal to what? This one plus this one. Okay, and because nu is minus, so 100 minus 60 become 40. And 300 minus 180 become 120. Okay, and this generate 120. Easy, right? So this is what we call fractional conversion. Right. Okay, now let's move to a ready example 4.6-1. Acrylon nitrile. Okay, acrylon nitrile. Acrylon nitrile is an important monomer for the manufacturing of useful plastics. Okay, it doesn't smell good. Okay, and it colorless liquids, but often yellow due to the impurity. Okay, so this acrylon nitrile can produce. This is kind of mass production. So this is kind of a lot of towel. You need to make these products. So the chemical reaction looks like this: C3H6 plus ammonium plus oxygen become this one, acrylon nitrile, and plus oxygen. Plus water. So in a chemical reaction, you know that you will lose the C3H6 will lose hydrogen, and then ammonia will lose hydrogen, and this put this carbon and nitrogen bond together. Okay. So before we talk about this topic, this acrylon nitrile is a key production materials for many products. Okay, these are the products we want to make. Okay, so just let you, this is just for your information. Right, so now let's please have the your text with me, and I want to talk, I want to go through this example with you together. Okay, so do you have, please have this with you, I mean the text, right, with you. So let's go, if you have a text, if you have a book, is in your book page 112, and then example 4.6-1, the title is reaction stoichiometry. Okay, so let's go through this. The alkaline long nitrile is an intermediate used in the production of the number of the polymers. Okay, including blah 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 blah. Right, and right. So as you can see that this chemical reaction equation showing you here. I don't want to. Just please take a look by yourself. So let's go to the question. The second paragraph. The feed to the propylene ammonium dioxidation process contain 10 moles of the propane, 12 moles of the 12% ammonium, and 78% air. A fractional conversion of the 30% of the limited reactant is achieved. So first of all, you need to decide which one is limited reactant, right? So when you take a look of this equation, can you tell me which one might be the limited reactant? A, C3H6, B, NH3, C, O2, D, none of them. Which one? Have a guess. When you think of these three reactants, which one you will think is might be likely to be the limited reactant? Which one? You think which one is more expensive? It should be C3H6, right? This will be a more logic, which is a limited reactant. But we don't know because, you know, we have some information about 10 moles, 12 moles, and then other with 78% air. So if you have 10 plus 12 plus 78, that will be 100%. So we don't know, you don't know which one is the limited reactant, but if you guess in a common sense, using your common sense, the C3H6 might be the limited reactant. Okay, but anyway, the fractional conversion of 30% of the limited reactant is achieved. Also, this is one of the specification, right? Okay, the taking 100 moles of the feed as a basis determine which reactant is limited, and the percentage by which of the other reactants is in excess, and the molar amount of the all products gas constituent for the 30% conversion of limited reactant. Okay, so there's 30% conversion. Okay, right. So here I already finished reading this information to you. So please take a look of this slide on the wall here. So after we read the text, we understand this is chemical reaction here. Okay, C3H6 plus NH3 have the oxygen, and the O2 becomes C3H3N and H2O. So before the reaction, you understand that we have 10 moles. You know, the basis is 100 moles. So the 10%, that means the 10 moles, right? How about ammonium? It's 12%, that means 12 moles. And then we have 78% of the air, right? And 78% of the air means 78% air, but you know, there are only 21% of the oxygen in the air. So if 78 need to times 0.121, that means 16.4 here. Okay, and then in the beginning you don't have this one. This one will be 0 and 0, right? Okay, so the question 1 is that which one? There's 3 reactants, C3H6, NH3, and O2. And which one is the limiting reactant? According to the things you know, there's 10%, 10, 12, and 16.4. You had to count according to what? Stoichiometry ratio, right? So stoichiometry ratio tells us that find the limiting reactant. If you have, this need to be 1 mole, and this need to be 1 mole. So if you have a n moles of the ammonium divided by moles of the C3H6, it need to be equal to 1. If it is more than 1, that means what? That means ammonium is excess reactant, right? Because ammonia has more. So when you do the calculation, the 12 divided by 10 here is larger than 1. That means what? Ammonium is a limited reactant if you do the comparison of these two, right? If this consume 10, this ammonia need to consume 10 moles, and you have 2 moles left. So these 2 ammonium will be the limited reactant. Okay, sorry, will be the excess reactant. So C3H6 will be the limited reactant. And now, if you take a look of this and this, right? Oxygen, the moles of oxygen divided by moles of the you need to divide by moles of the oxygen divided by moles of the C3H6. You need to be what? 1.5, right? Need to be 1.5. If this is larger than 1.5, that means what? This is limited reactant. This is excess reactant, right? So once you do the calculation, that will be 16.4 divided by 10, and it's larger than 1.5. Okay, so oxygen is a limited reactant. So if you do this compared to these two, ammonium will be limited reactant. If you compare to these two, oxygen will be limited reactant. So excess reactant. So this one will be definitely limited reactant. Okay. So C3H6 will be limited reactant. And then according to, we understand the fractional excess of reactant will be, you can write down the fractional excess of reactant, which is O2 and the ammonium, right? So could you please tell me what's the number of this? Fractional excess of NH3. If you know the definition, the fit will be 12, right? And stoichiometry will be what? 10, right? So as you know, that will be 12 minus 10 divided by 10. That means what? 20% excess of the ammonium. Then how about oxygen? I'm sure you can do this for me, right? You can do this for me. That will be 9.3%. This is fractional excess. Okay, and then the text tells us that the specification is that C3H6, the fractional conversion is 30% only. Actually, that means what? 10% only consume what? 10 moles only consumes 3 moles only, right? Limited reactants. So limited reactant only reacts 30%. So that means what? After reaction, the 10, minus 1 is nu, right? Nu. And then 10 is moles times 0.3. This is what we call XC, right? XC, 0.3. So actually reaction is minus 3 here. And how about this one? It's minus 3, right? It's minus 3. Okay, how about this one? It's minus 4.5. How about this one? I'm sure you don't know that. 3 and 3 and 5, sorry, 9. So this is plus, this is minus, minus. So as a result, you know, after reaction, now it'll be 7 and 9 and 11.9 and 3 and 9. So this is not an ideal reaction because you want to compute all of this. But unfortunately, because some reasons, because the reactor is not too good, or because of the time limitation, and you don't want to complete this reaction. So the conversion, fractional conversion is only 30%, which is quite low. But anyway, so this is the final number. Okay. So as you know, input, if you do the mass balance according to this equation, you have 4 inputs. 1, 2, 3, 4. 1, 2, 3, 4 here. And how many outputs do you have? You have 6 outputs. 6 species in the output stream. Okay, so be careful when you do the mass balance. As long as you know the definition of the, like, fractional conversion, limited reactance, excess. Okay, all you know is final moles equal to initial moles times plus nu times xc. Very important. Okay. Right. So the next topic will be 4.6c, chemical equilibrium. So what is chemical equilibrium? You know, as a chemical engineer, you need to know important 2 things. The first is called chemical thermodynamics, 化工热力学. Actually, another one is chemical kinetics, 化工动力学. So when I was young, my professor told me, you only need learn 3 things in a chemical engineering. First one, 输送现象. Second one, 化工热力学. Third one, 化工动力学. That's it. Finish. 输送现象 means including unit operation. That's it. So what is thermodynamics? It's something to do with energy. But what we want to learn is we don't care about something happen during the time. We just want to know what's the initial stage and what's the final stage. So what will be the final composition of the reaction mixture? It can be reaction. It can be it can be a physical process. So what you care is initial stage and the final stage. That's what we call thermodynamics. Okay, thermodynamics. 热力学. How about kinetics? 动力学. 动力学, chemical kinetics is related with time. You want to know what's going on during the process. So the second one is first second, first day, first hour, first day, and then final. So you want to know what's going on during the process. So the chemical kinetics always related with time. The thermodynamics, nothing to do with the time. You just care the first stage and the final stage. Okay? This is chemical thermodynamics and the chemical kinetics. Okay? And then chemical reaction engineering. And another term is called irreversible and reversible reaction. I'm sure you know this already. So irreversible means what? Single direction. For example, if this is irreversible, okay, the SO2 plus oxygen become SO3. This is irreversible. Okay, single direction. So the balance is that the concentration of the limited reactant eventually approach to 0. So this one, if this is the limiting reactant, for example, SO2, eventually it reach to 0. Okay, it can be 1 second, it can be 1 year, it can be 10 years. It depends on how fast is the chemical reaction, right? So if we plot something like this, the y-axis is chemical reaction, the x-axis is chemical reaction time. It can be like this, or it can be like this, very fast. It can be like this. It takes a long time. Okay, but eventually reach to 0. Eventually reach to 0. So this is irreversible reaction. How about reversible reaction? Reversible, this is one of the example of a reversible reaction. C2H4 plus H2O become C2H5OH. This is reversible. Reversible means what? It can be, chemical reaction can go from left to the right, what we call A path, A direction, or A path here. And then it can be from the right to the left. That's regarded as a B path. Okay, so again, let's plot the reaction rate and versus the reaction time. It can look like this. It eventually reach to equilibrium. That means that the speed from left to the right and the speed from the right to the left will be equal. And this is what we call reversible reaction. Okay, so it can be one when you reach equilibrium. That means it can be 1 second, it can be 1 hour, it can be 1 day, it can be 1 year. Okay. Right. So do we have time? Yes, we do. So example 4.62, 4.6-2. Actually, this is quite easy. So let's go through this. Please have, I'm going to read the text with you, and so please have this, have your text with me, with you together. So calculation of the equilibrium composition. So so this is called water gas shift reaction. The C2 plus H2O becomes CO2 plus H2O, H2. Okay, and we know the equilibrium constant is this, which is T time. T is the function of T, right? Using the Kelvin. And the mole fraction of the 4 species satisfy the relations. You know that, right? When you are in high school, the fraction of the carbon dioxide times the fraction of the hydrogen divided by the fraction of the carbon monoxide times the fraction of the water is equal to K. K is the is a constant, right? Equilibrium constant. So this was in 1105 Kelvin, and K equal to 1. Right. So please take a look of this with me on the slide here. So we have CO and H2O and the CO2 plus oxygen, right? So in the very beginning, we have 1 mole of the carbon monoxide. We have 2 moles of water. We have 0 and 0 here, right? And during the reaction, let me tell you that during the reaction, we don't know how many is reacted. So we know we just want to write -1 times Xe because we don't know the extent of reaction, right? And then we want to know that this is -1. this which is external reaction. And then could you please tell me how to write down here? 1xe, right? 1xe. And this is 1xe. 1x. Okay? And then what happened to the after reaction? Now be 1 plus this one, right? 2 plus this one. 0 plus this one, and 0 plus this one. The only specification we know is that the equilibrium constant is 1. K is equal to 1 at a certain temperature and pressure. So the question we want to ask us is what is the external reaction here? Okay. So let's say that if we plus these 3 together, if we plus these 4 numbers together, that means the total is 3 moles, right? If you minus 1xe, minus 1xe, plus 1xe, plus 1xe, if you put these 3 together, 4 together, that will be total is 3 mole. And we all understand the equilibrium constant is equal to 1. So the question asks us, what is the xe here? And we know that K equal to the fraction of carbon dioxide times the fraction of the hydrogen divided by the fraction of mono dioxide and fraction of the water, right? So let's write down here. So this is the fraction of the carbon dioxide. Why? Because you have 3 and xe, right? Okay. Oh, sorry, 3 and xe here, and 3 and xe here. This is products, and this is reactants. Reactant is what? 3, because total is 3, right? And this is 1 minus xe times what? 2 minus x divided by 3. Okay, and this is equal to 1. So if you rearrange this part, you can get things like this. And obviously, you understand this is 一元二次方程式 right? 一元二次方程式 is quadratic equation. Quadratic equation. And obviously, you know that you can easily to solve this quadratic equation. And xe will be 0.667. So when you get xe, you got that, you will understand what's the final products, what's the moles of the final products, right? Okay, so the question asks us, what's the fractional conversion of limited reactant? Carbon monoxide. Could you please tell me? Fraction conversion is reactive feed, right? So that will be equal to, because because we have reacted is 0.667 and we feed 1 more. So that will be the answer. Okay? So this is a quite easy question. So I want you to practice by yourself. The next topic will be 4.6d. We want to talk about multiple reaction. You know, so far we only talk about single reaction only. And we don't talk about multiple reaction. And it's more complicated because it involves yield and selectivity. Okay? And I'm going to leave this topic to the next week. So that's it for today.